Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples calculating bending stress and bending moment of inertia. In this video, we're continuing a problem that we started in the previous video. We're asked to calculate the centroid, the moment of inertia about z, and the normal stress on the bottom of the flanges due to an applied moment of 1.05 kilonewton meters. We found the centroid in the last video, and it's denoted here on the figure. Centroid location is 27.49 millimeters from the bottom and 12.51 millimeters from the top. Next, we should compute the moment of inertia. In order to calculate the moment of inertia about the overall centroidal axis, we'll apply the parallel axis theorem. This theorem says that the overall moment of inertia, Iz prime, equals the moment of inertia of each section about its own centroid, plus the area of the section times the distance, d squared, from each individual section's own centroid up to the overall centroid. I'll show you how this is illustrated, or how this is calculated. In order to do this, we break the section up into different segments, which are composed of rectangles. We call section 1 this top rectangle right here, okay, and section 2 and 3, which are basically identical, are these two little rectangles on the side. Okay, and we can calculate their area and the locations according to the dimensions given. The approach that we like to take for calculating moment of inertia is to summarize our calculations in a table. So we'll create a table in this case. Okay, we want to calculate for each section, so label them 1, 2, the 1 being the web, 2 and 3 being the flanges on the side. For each section we want to calculate I, and the units are millimeters to the fourth. We want to calculate d sub I in millimeters, the distance from the section centroid to the overall centroid. Then we calculate d sub I squared times a sub I in units of millimeters to the fourth. And finally, we'll calculate Iz prime, which is, in this case, is going to be the sum of the first column and third column. And then in the end, we'll add them all together to get the overall centroid. Okay, so let's start with section 1. We need to calculate I for section 1, which is bh cubed over 12. In this case, we'll take b as 75 millimeters, the h as the 6 millimeters, and cube that. That leads to an I of 1350 millimeters to the fourth. Then we need to find d sub I, and d sub I, if I draw it here on this section, is the distance from the overall centroid, okay, to the centroid of that section. That's d1. And we can calculate d1 as 12.51 millimeters minus this half the thickness of the flange, minus 3. So that would be 9.51 millimeters. So I'll put in d as a 9.51. Okay? Then d sub I squared times a sub I. We computed a sub I in the previous video to be 450 millimeters. Multiply that by d squared is going to give 40,698 millimeters to the fourth. Adding the first and the third column, we get an Iz prime of 42,048 millimeters to the fourth. Okay? Sections 2 and 3 are going to be the same. Let's start by calculating their moment of inertia, bh cubed over 12. This time we take the thickness of 6 millimeters as b, and we take the length of that section, which is 40 minus 6, or 34. We'll call that h. So our I is computed as 6 times 34 cubed over 12, which is 19,652. Okay, d sub I for this section would be from the centroid of the section to the overall centroid. That's d2. And we can calculate d2 as the overall centroidal distance, 27.49, minus half the height of that section, which is 17, and that leads to 10.49 millimeters. So 10.49, 10.49. D sub I squared times A sub I is going to be 10.49 squared times the area of section 2, which was 204, and that leads to 22,448. Same for both, 22,448. Same for both sections 2 and 3. And finally, adding the first column and the third column, we get an overall I of 42,100 for both sections 2 and 3. Now when we add all three of these together, so add this column together, the result is 126,248 millimeters to the fourth. Okay, and if we were presenting that as our overall answer, we might want to reduce the number of significant digits, but it's okay for this case. Now to calculate the stress, we'll use the formula sigma equals negative m y over I. I'm actually going to drop the sign and determine it by inspection. To calculate at the bottom of the section, I want to take y equal to c at the bottom divided by IZ. And my working units are going to be newtons, millimeters, and megapascal, because a megapascal is a newton per millimeter squared. So go ahead and substitute sigma equals the moment 1.05. To convert that to newton millimeters, I'm going to multiply by 10 to the 6th. Then my C bottom value is the distance from the centroid to the bottom, 27.49 millimeters. And I divide by the moment of inertia, 126,248 millimeters to the fourth. We can check millimeters squared on the top cancels with millimeters squared on the bottom, and our overall units are newtons per millimeter squared or megapascals. So sigma bottom equals, that computes to 228.6 megapascals. And the last thing is the sign. By inspection, I'm applying a positive moment, so that's going to cause my beam to bend upward in a smile, and as a result we'll have tension on the bottom and compression on the top. So stress at the bottom is going to be tensile or positive. And as a sanity check, in my moment of inertia, I know that my inertia terms for the individual sections, the ones that are oriented vertically, much larger than the one oriented horizontally, but the di squared times a is larger for the section on the top than the sections that pass through the centroid. So those numbers seem to make sense. My stress is a fairly large number, but within the reasonable range for engineering units, less than 300 megapascals, which is the start of where yield might occur. So these are reasonable values. I believe that my answer looks correct.